Dear participants, welcome to my presentation. I am Baran Özyurt from Ankara University Chemical Engineering Department. Today I'm going to talk about my study subject, degradation and mineralization of methyl orange by advanced oxidation processes. First of all, let's start with a brief introduction. The production, use and disposal of many commonly used dyes release pollutants. The dye-based pollutants are reported as persistent in aquatic environments and have potential adverse effects on health. Among these dye-based pollutants, methyl orange is also known as a pH indicator used in laboratory, industry, and microbiology. Is also used as a coloring agent in materials such as plastics, rubber, and paint. In our study, we have chosen this as our target pollutant. Methyl orange is reported to be resistant to biodegradation. It has teratogenic, carcinogenic, mutagenic, and toxic properties. Therefore, effective, economical, and sustainable treatment technologies are required to treat these pollutants. Advanced oxidation processes stands out as a treatment technology for these kinds of dye-based pollutants. These processes can oxidize many pollutants in water. Their effectiveness is evaluated based on the yield of their hydroxyl radical production, which is one of the strongest oxidizing agents ever reported in the literature. Various mechanisms have been proposed based on how these radicals are generated. Advanced oxidation processes are classified based on how the oxidizing agent is activated. Among the chemical advanced oxidation processes, Fenton process is a good example. Here we use ferrous ions to activate hydrogen peroxide to produce hydroxyl radicals. This process has some disadvantages. Photochemical advanced oxidation processes are another alternative. Photophantom process is another photochemical advanced oxidation process. Here we have some advantages compared with phantom process, such as the regeneration of the catalyst by means of the UV light irradiation. Here ferric ion is converted to ferrous ion. Then therefore we can have additional hydroxyl radical production. Heterogeneous photocatalysis is another alternative for advanced oxidation processes. Here titanium dioxide can be used to produce hydroxyl radicals. Electrochemical advanced oxidation processes are another alternative method. Electrophantom process is a good example of electrochemical advanced oxidation processes. Here we activate oxygen in the water with cathodic reduction to produce the oxidizing agent hydrogen peroxide, and also the phantom catalyst is regenerated on the cathode as well to perform phantom reaction. Photoelectrophantom process is developed to overcome this kind of disadvantages of electrophantom process, and also its heterogeneous alternative has the advantages of no sludge generation, expanded pH range, and photodecomposition of ferric carboxylic acid complexes, and also it generates additional hydroxyl radicals. Here, as we can see, with the irradiation of ultraviolet light, ferric ion carboxylic acid complexes are decomposed to ferrous ions, and some of the carboxylic acids are mineralized. Photoelectrocatalytic process is also proposed as an alternative method, which includes in situ production of hydrogen peroxide with the cathodic reduction of the oxygen and its conversion to the hydroxyl radical with the UV light irradiation. In our study, we have compared photolysis, photocatalytic degradation, photoelectrocatalytic process, phantom, photophantom, electrophantom, photoelectrophantom, and heterogeneous photoelectrophantom processes for the degradation and mineralization of methyl orange. We have performed our electrocatalytic, photoelectrocatalytic, and photoelectrocatalytic processes in a 100 milliliter cylindrical glass cell, which contains 80 milliliters of 0.1 millimolar methyl orange, and in the electrocatalytic process we have used 50 millimolar sodium sulfate as supporting electrolyte. We have used platinum anode and carbon felt cathode in our electrochemical processes, where with the constant current of 100 milliampere conditions. And also in the photocatalytic processes we have used a 6 watt UVA lamp with a 365 nanometer wavelength. Concentrations of methyl orange is measured spectrophotometrically, and mineralization was monitored by chemical oxygen demand analysis. We have started our degradation and mineralization studies with the comparison of photochemical advanced oxidation processes. According to the results, there is no degradation by means of photolysis. When we used photocatalytic degradation, nearly 35% of the methyl orange is degraded within a 1 hour process, whereas we have completely degraded the methyl orange with photoelectrocatalytic process within 35 minutes. Among their mineralization efficiencies, photocatalytic and photoelectrocatalytic process yields nearly similar mineralization efficiencies. When we have compared electrochemical advanced oxidation processes, electrophantom and photoelectrophantom process has yielded higher degradation efficiencies. They have nearly completely degraded the methyl orange within 15 minutes, and in 1 hour mineralization study we have seen that the photoelectrophantom process has the highest mineralization yield, which has removed nearly 80% of the chemical oxygen demand of the methyl orange process. When we have also compared the mineralization current efficiency, we have seen that the photoelectrophantom process has very high mineralization current efficiencies. When we have compared all the phantom-based advanced oxidation processes, we see that traditional phantom and photophantom processes has the highest yields for the degradation of methyl orange within nearly 6 minutes. Of course, these processes represents the experimental maximum values to us. The nearest approximate to these traditional processes was the photoelectrophantom and electrophantom processes respectively. When we compare the mineralization efficiencies within 1 hour, we see that photophantom process has the complete mineralization of methyl orange, whereas phantom process mineralized nearly 90% of it, followed by the photoelectrophantom with the nearly 80% mineralization. To conclude, when we combine all the treatment results all together, we see that phantom-based advanced oxidation processes stands out among the other advanced oxidation processes. Photoelectrophantom process showed promising performance for more sustainable process operation And we can say that titanium dioxide magnetite composite catalysts may be a good alternative for the development of more efficient heterogeneous photoelectrochemical treatment processes. These are the references are used in this study, and thank you for your attention.